Welcome back to the deep dive. Today, we're tackling something that you sent us a ton of sources on, and it's one of the biggest challenges in all of modern tech: power efficiency.
Yeah, and we're not just talking about, saving a few milliamps here and there.
No, this is about the core discipline of designing digital systems that are just fundamentally thrifty from the ground up.
It's a huge topic with massive real-world consequences. Power efficiency has it's completely shifted from being this secondary thought, sort of nice to have, to a primary non-negotiable metric for any design.
Absolutely. And you can see these two sort of unrelenting forces pushing on it. On one side, you've got all the portable electronics,
Maybe your smartwatch.
your smartwatch, your fitness tracker, where battery life is literally everything. We demand days, not hours, from these tiny little things.
And then on the complete other end of the spectrum, you have the massive hyperscale data centers, the
Mhm.
cloud. Their power bill is just astronomical.
It's escalating so fast. So for them, it's about thermal management, sustainability, and just sheer economics.
For sure. If your technology isn't low power, it's just not competitive anymore.
Mhm.
Simple as that.
So, our mission today is to dig into the specialized techniques, the real art of this, that let engineers get these massive power savings. And the sources all point to one thing: the best results come from a hierarchical, top down approach. Okay, let's unpack this.
So before you can optimize anything, you first have to know where the power is even going. The total average power a circuit uses, what we call P average, is really a sum of four different types.
Four types. Okay.
Yeah, you've got switching power, then there's short circuit power, linkage power, and static power.
That sounds like we could be chasing a lot of tiny leaks. Where's the real focus? Where do we put our energy, so to speak?
The big one, the main target for any designer is definitely switching power. P switching.
Okay.
When a digital circuit is active, when it's actually working and flipping bits, switching power is the dominant force. It can be, roughly 65% of the entire energy budget.
65%. So if you can make a dent in that, you're getting huge savings across the whole system.
Disproportionate savings, exactly. It's the biggest piece of the pie.
And to get at that switching power, we have to look at what defines it. The sources lay out this core equation with four key factors, four levers we can pull.
Right. And it looks a little intimidating at first, but it's totally logical. Let's walk through those four variables that define P switching.
Okay.
The first one is alpha. That's the switching activity. It's a measure of how many times a node in your circuit, on average, flips its state per clock cycle.
So that's based on the logic you're using and the kind of data running through?
Exactly. More activity means a higher alpha, which means more power.
Okay, what's next?
Next up is CL, which is the load capacitance.
Huh.
The easiest way to think about this is just the physical size of your circuit.
So longer wires, bigger transistors.
Yep. All of that contributes. It's the total capacitance at a gate's output. A bigger circuit means a higher CL, and your power use goes up linearly with it.
Then you have F, clock frequency. That one seems pretty straightforward.
It's the most intuitive one for sure. That's your clock speed. You double the frequency, you double the power consumption. It's a straight one-to-one relationship.
So we have three variables that are all linear, but the sources are really, really clear that one factor is just way more important than all the others, and that's VDD, the supply voltage. Why is that the big hammer for designers?
What's fascinating here is it's just the physics of it. Unlike those other variables, the supply voltage isn't linear. It's a quadratic lever. Power scales with VDD squared.
Wait, I want to make sure everyone listening really gets that. If I design a system where I can lower my operating voltage by, let's say, 20%, I don't get a 20% power saving, do I?
Not even close. You get a massive return on that investment. You
Yeah.
cut VDD by 20%, you end up cutting your switching power by almost 36%.
36. Wow.
That exponential relationship, that VDD squared effect, is why the entire art of low power design is built around finding clever ways to push that voltage as low as you possibly can.
So that quadratic impact is the goal. But the sources say you don't start by tinkering with the voltage regulator. The top-down approach says the biggest savings actually start at the highest level of abstraction.
That's exactly right. You have to think of the design process like a funnel. Level one, the widest part, is algorithmic optimization. This is where you filter out the work from the very beginning.
You choose the smartest path before you even think about code or hardware.
Right. The biggest wins come from choosing an algorithm that just fundamentally requires less computational work to get the job done.
And there's a really important subtlety here, isn't there? It's not just the number of operations.
No, it's the weighted cost of those operations.
Yeah.
Some math is just heavier than other math. It's more expensive.
For instance.
Divisions and square roots. They consume a lot more energy than, say, a simple addition or a bit shift. They're computationally expensive.
And the sources have a great case study for this, solving that linear equation, y equals phi times x. There are two very different ways to do it.
Yeah. If a designer just goes with the classic method, Gaussian elimination, they end up with a huge number of divisions, specifically n times n plus 1 over 2 divisions.
And because divisions are so power hungry.
You've locked yourself into a power-intensive architecture before you've even started.
But there's a better way. The modified Koleski factorization, or MCF.
Exactly. MCF gets you to the same answer, but with far fewer of those extensive operations. You might only need, say, n divisions and n square roots. The final architecture is just inherently more power efficient because the underlying math avoids the costly steps. That's level 1 optimization.
So once the core computation is lean, level 1 also looks at how we move data. This is where we can attack that alpha variable, the switching activity.
Right. Every single bit that flips from 0 to 1 or 1 to 0 consumes a little bit of energy. On a busy data bus, that adds up incredibly fast.
And a classic technique to reduce that is something called gray coding.
It's elegant, really. It just ensures that when you're counting up or down, only a single bit changes between any two consecutive numbers.
So instead of going from, say, 7 to 8 in binary, which is 0111 to 1000,
which is 4-bit flips. A big burst of energy.
with gray coding, that same step would only be one flip.
One flip. You've just cut the power for that transition by 75%.
That's a preventative measure, but the sources also talk about a more active, sort of defensive technique called bus inversion coding, or BIC.
BIC is really cool. It's adaptive. The system basically watches its own energy use. Before it sends a word across an n-bit bus, it calculates how many bits would have to flip from the last word.
That's the Hamming distance, right?
That's the Hamming distance. And if that number of flips is more than half the width of the bus, so more than n over 2, it doesn't send the original word.
So what does it send instead?
It sends the bitwise inverse. It flips every single bit, and then it sends one extra little polarity bit to tell the receiver, hey, what I just sent you is inverted. By doing this, you mathematically guarantee that the number of bit transitions can never be more than half the bus width. It actively caps that alpha value.
Okay, so we've made our algorithm as lean as possible. That's level 1. Now we move down the funnel to level 2, architectural optimization.
And this is where we finally get to cash in on that VD squared prize we talked about.
Right, this is where we create the timing room to actually lower the voltage.
Level 2 is all about a trade-off. You trade a bit more hardware for the ability to run at a lower clock frequency, or...
And slowing down the clock does two things. It gives you a linear power saving, but more importantly, it creates what's called timing slack.
And that slack is the currency you use to buy voltage reduction. You cash in that extra time by lowering the supply voltage, VDD, and because the savings are squared, that trade is always, always worth it.
The sources outline two main ways to create the slack: parallelism and pipelining.
Let's start with parallelism. Imagine a basic serial architecture is like a single highway lane. To get all the cars through, it has to run really, really fast. A high clock speed, which demands a high voltage.
And a parallel architecture is like adding more lanes to the highway.
Exactly. You literally duplicate the hardware block so you can process, say, 2 data samples at the same time. Now your clock only needs to run at half the speed to get the same overall throughput.
Which creates that slack.
Which creates the slack to slash VDD. Yes, your total capacitance, CPAR, goes up a bit because you have more hardware, but the VDD squared savings just dwarf that tiny cost.
Then there's pipelining, which is a bit different. You're not adding lanes. You're, breaking down the journey into smaller segments?
That's a great analogy. Pipelining attacks the circuit's critical path, the longest possible delay. By inserting registers to break that long path into smaller sequential stages, you reduce the time needed for any one stage.
So the whole system can be clocked faster, or, for our purposes.
Or you can maintain the same throughput at a much lower clock frequency. And again, lower F means lower VDD. Pipelining often lets you be even more aggressive with voltage scaling.
Level 2 also gets into transformations inside the blocks themselves, like operation substitution.
Right, this is about avoiding overkill. If your code is doing a simple multiplication, say y equals c times x, where c is a fixed number.
A constant.
A constant, yeah. Don't use a massive general-purpose multiplier that can handle any two numbers. It's just a huge waste of energy.
Instead, you substitute it.
You substitute it with a specialized low-power circuit built just for that one multiplication. something like a shift and add network. It's tiny, it's simple, and uses way less power.
And what about glitches? The sources talk about these as a form of digital waste.
They are pure waste. A glitch is a spurious, unnecessary transition. It's when a signal flips back and forth a few times before it settles on the final correct value.
And that's caused by signals arriving at a gate at different times.
Exactly. Unbalanced signal paths. You fix it by restructuring the logic. You might replace a long, glitchy chain topology with a balance tree, which makes sure all the inputs arrive at the same time, preventing those extra wasteful flips.
There's one last fascinating piece in level 2, and it's about data representation. The trade off between two's complement and signed magnitude.
Oh, yeah. This is a beautiful example of a power versus complexity trade off. If you have data that crosses zero a lot, like audio signals or sensor data,
Mm.
two's complement is actually pretty inefficient. For an 8-bit number, going from -1 to 0 requires all 8 bits to flip. That is the maximum possible switching activity, a huge power spike.
How does signed magnitude help there?
In signed magnitude, that same transition from -1 to 0 only requires 2 bits to flip, the signed bit and the least significant bit. The power saving for that one specific case is enormous.
But there has to be a catch.
The catch is that doing math with signed magnitude numbers requires much more complicated hardware. So you save power on the switching, but you pay for it with more complex logic. That's why two's complement is still the standard for general purpose computers, where arithmetic speed and simplicity are usually more important.
Which brings us down to the very bottom of the funnel. Level 3, gate level optimization, the fine tuning.
This is where we eliminate waste from circuits that are just sitting there turned on but not doing any useful work.
And the star player here is clock gating.
The undisputed star, yeah. Think about the Wi-Fi chip in your device when you're not connected to Wi-Fi. There's no reason for its clock to keep ticking and refreshing all its internal registers. It's just burning power for nothing.
So clock gating is literally putting a gate on the clock signal.
That's exactly what it is. You use some simple control logic, often just an A and D gate, to completely turn off the clock signal to that inactive block.
And the impact is?
It's absolute. The moment that clock is disabled, all the switching activity stops. The dynamic power consumption in that block drops to zero, completely, until it's needed again.
So if we look back up at the whole funnel, this top-down strategy has let us systematically attack every single variable in that original power equation.
If we connect this to the bigger picture, that's exactly what's happening. Level 1, the algorithm, targets alpha through smart computation and data coding. Level 2, the architecture, is all about create the slack to attack GFAC, and most importantly, VDD. And level 3, the gate level stuff, is a final precise attack on alpha by killing wasted switching.
It makes it so clear that you can't just add power efficiency at the end. It's not a feature.
That's the core realization. Optimal power efficiency is the result of a disciplined, power-aware methodology at every single design stage, from the highest level of abstraction all the way down to the individual gate.
So the key takeaway for you listening is that the really massive power savings don't come from the small fixes at level 3. They come from those high leverage decisions at levels 1 and 2 that fundamentally reduce the amount of work the chip has to do in the first place.
It all starts with the choice you make at the drawing board.
We focus today on digital systems, but that VDD squared rule, where a small change in an input gives you a squared change in the power cost, that's a really compelling bit of physics. So here's a thought for you to explore on your own. Where else in the physical world, outside of silicon, might a small linear change in some input variable lead to a squared or even cubic change in the output or the cost or the energy used? Something to mull over until our next deep dive.